In this lesson, we will explore the properties of gases and how their behavior can be described using several fundamental gas laws. We'll examine how gases respond to changes in temperature, pressure, and volume. We'll learn how heating a gas makes the particles move faster and farther apart, how cooling them slows them down, and how changing the pressure affects their volume. By the end of this lesson, you'll be able to explain the relationships among temperature, pressure, and volume, and apply Charles's law, Boyle's law, Gay-Lussac's law, and the ideal gas law to real-world situations, like why a can collapses when cooled, or how weather balloons expand through the atmosphere. So, heating a gas causes the particles to move more rapidly and increases the distance between them. So here we have a balloon. It's at an initial temperature and pressure, or volume and temperature. We're going to heat it up, which causes the balloon to expand. So now we have a new volume and a new temperature. One of the issues that people have with working with these gas laws is that it's very easy to get lost with all of these different variables and the subscripts and everything like that. So what I tell people to do is kind of focus in on the important units. So if you see something where the unit is liters or milliliters, it's talking about a volume. And if you see something where it's talking about degrees C or Kelvin, it's talking about a temperature. The way you keep the ones and the twos distinct is you kind of go through the problem and you say, all right, well, here's the first volume I found. Here's the temperature that goes with it. So that would be V1 and T1. And then you go and you say, all right, well, here's the new volume and here's the new temperature. It's just a matter of keeping the information organized. So the relationship that describes the volume-temperature relationship is called Charles's law. So it says for a closed system, so a fixed number of gas particles, the volume of the gas increases as the temperature increases. So it's a direct relationship. The equation is going to be V1 divided by T1 is equal to V2 divided by T2. So here we have all the information. We have an example. It says we're starting out with an initial volume of 2 liters and an initial temperature of 0 degrees Celsius. We want to find out what our new volume is, so that's V2, that's what we're looking for. And we have a final temperature of 20 degrees Celsius. So we're going to go ahead and substitute in the values into Charles's law. And then you have to ask yourself, what's wrong with this problem? Why would a math teacher be having a serious fit right now looking at the way this problem is set up? Hopefully you said, well, it's because we're dividing by 0. You're not supposed to do that. So we will go ahead and see what we need to do with our temperatures. So for all gas laws, you have to convert the temperature that you're talking about into the absolute temperature scale, because the absolute temperature scale does not have any negative values and it does not have a 0. Well, at least not a 0 that we're going to be working with. The way you do this is you take whatever it is in degrees Celsius and you add 273. So for example, convert 0 degrees Celsius into Kelvin. It would be 273 Kelvin. So looking back at the balloon problem and fixing the temperatures, now we're going to put the numbers back in there, cross multiply and solve for the new volume, V2, and you get that the volume is now 2.1 liters. When you're solving these gas law problems, it's really important that you do sort of a reality check. So you said, all right, we started out at 2 liters and we warmed it up, the volume increased. So that means that math is working today. We have done the math correctly. So another relationship is when you cool off a sealed system and you get a pressure change. So here we have a video. One of my students took it for me. And we are boiling some water in a can. So the water vapor is now at 100 degrees Celsius. And then we're going to invert the can into some ice water that's in this bucket so that we trap the hot gas inside of the can and then change the temperature rapidly. So we'll go ahead and do that. And it's not cooperating with me. There we go. Let me put it on pointer. Well, I can't figure out how to get the movie to run. So I'll just tell you what happens. So you invert the can into the cold water and the can will crush. Actually had a student one time, they managed to get the can to crush so that it was almost like it had been spiraled in on itself. All right, so going ahead, we're talking about Gay-Lussac's law. This is the pressure and temperature relationship. So for a sealed system, the pressure increases as the temperature increases, another direct relationship. This is why you should never put like aerosol cans into a fire, because there's a little bit of gas left over inside the can. The increase in temperature will cause the pressure on the inside of the can to increase rapidly, and the can will end up blowing up. So the important units, when you're talking about temperature, just like it was before, degrees C or Kelvin. With pressure, there's a lot of different units that get used. The one that is most common is the atmosphere. Right now we're under 1 atmosphere worth of pressure. The official metric unit is the kilopascal. It's actually the pascal, but everybody uses kilopascals. And some older units would be millimeters of mercury and torr. So for the purposes of the kinds of problems that we're going to be using, for the most part, you just need to be able to recognize that when you see one of these, it's talking about a pressure.
Yep.
Yeah.
Oh, now it goes.
Oh, wow. Damn.
All right, so let's calculate what the final pressure was inside of the can. So we started out, we were under 1 atmosphere of pressure. Remember, the water was boiling, so that meant that we had a vapor pressure of 1 atmosphere. It was boiling, so our temperature was 373 Kelvin. We're looking for the final pressure, and then we put it into a bucket of ice water, so the final temperature was 273 Kelvin. We write down Gay-Lussac's equation, fill in the numbers, solve for P2, and we get that as a result of that change in temperature, the pressure on the inside of the can is now like 3/4 of an atmosphere, which is why the can crushes, because the pressure on the outside is much higher than it is on the inside, so it's squishing it down. All right, so this is supposed to be a piston chamber. It looks kind of like tadpoles swimming around in a container. And we have an initial pressure and an initial volume. And then afterwards, we allow the piston head to fall, causing the volume to be much, much smaller. So Boyle's law is for the pressure and volume relationships. It says for a closed system, the pressure increases as volume decreases. So this is an inverse relationship. And the equation is P1 times V1 is equal to P2 times V2. And then the important units, pressure, we have that assortment of different units, just need to be able to recognize them. And we have volume is going to be liters or milliliters. So the pressure is caused by the gas particles colliding with the walls of the container. So pressure is going to increase as you have more particles, or perhaps as you decrease the, the amount of space that those particles can move around in. And right here, it just defines the different units of pressure again. So here's our example. We have a sealed can. It contains 1 liter of a gas at 101 kilopascals. So there's our V1, there's our P1. Wants to know what the pressure will be if the volume is decreased to half a liter. So there is our V2, and we're looking for P2. So write down all the numbers. I find it's very helpful to get the numbers out of the word problem, because the word problems tend to be a lot of visual noise and it kind of distracts people. So we're going to go ahead and plug the numbers in and solve for P2, and we get that as a result of cutting the volume in half, we have doubled the pressure. All right, then we have the combined gas law, and this is when you have temperature, pressure, and volume changing. So here we have the example. We got a diver. He's up at the top of at the surface of the lake. He goes down to the bottom of the lake, and we have a whole lot of words. So let's extract out these numbers. So we are starting out at a pressure of 1 atmosphere. The diver's lungs are 2.2 liters, and the temperature is 303 Kelvin at the surface of the lake. We dive down to the bottom of the lake. Now we have a pressure of 2.5 atmospheres being exerted on the diver, just a result of all of that water pressure. We're looking for what the new volume is, and the temperature at the bottom of lakes is going to be 4 degrees Celsius, 277 Kelvin, because that's where water is at its densest. So we write down the equation. That's combined gas law. So pressure 1 times volume 1 divided by T1 is equal to pressure 2 times volume 2 divided by temperature 2. Plug the numbers in, cross multiply, and solve for the new volume of the diver's lungs. And you can see that his lungs volume has been decreased to 0.8 liters. 0.8 liters. So again, the important units, we've got this assortment for pressure. We have volume is going to be liters and milliliters, and then temperature is degrees C or Kelvin. All right, so all of those were for a sealed system, so you had a constant amount of gas particles present. So let's talk about what you do when you have a change in the number of particles or a change in the mass. So whenever you have mass or the number of particles involved in actually doing the calculation, that means you have moles present. You're going to be using the ideal gas law. So this is pressure times volume is equal to number of moles, N is for number of moles, times R, which is the gas constant, just a number, times temperature in Kelvin. So there's a lot of different values for the gas constant. So just to make things easy, I always do my problems with the pressure in atmosphere, ideal gas law problems, with the pressure in atmospheres. The volume has to be in liters. Number of moles is going to be number of moles. And the temperature, of course, is going to be in Kelvin. When all of these things are true, then we can use R is equal to 0.0821. Do not worry about what the units look like. I've had a lot of people try to multiply things together when they see this liter times atmospheres. Just focus in on the 0.0821 value. So we want to know what's the volume of 1 mole of helium at 0 degrees Celsius in 1 atmosphere, which actually happens to be the standard temperature and pressure. So we write down what we know. And then we substitute in the numbers, solve for the volume, and we get that conversion factor from Moletown. And the reason why we have that particular conversion factor is that at STP, because those particles, when they're in the gas phase, do not interact with each other at all, they are independent of what the gases are. So 1 mole of air is going to have the same volume as 1 mole of helium, 1 mole of argon, 1 mole of carbon dioxide gas. It does not matter at STP. It doesn't matter what the substance is made of. All right, so the one that most people like the best is Dalton's law of partial pressures. It just says that if you have a mixture of gases, the total pressure is equal to the sum of the individual pressures. So for example, if you had 3 gases, the total pressure, and my abbreviation for total is TOT, is equal to the pressure from gas 1 plus pressure from gas 2 plus the pressure from gas 3. So the example in this case was the Earth's atmosphere consists of a mixture of nitrogen, oxygen, and argon. What's the partial pressure of each gas if the total pressure is 0.95 atmospheres? So you say, all right, well, 75% of the total, 78% of the total is going to be from the nitrogen, So you do the math. So 0.78 times 0.95, and you get 0.74 atmospheres worth of nitrogen. Finish it off for the other ones. So 21% is oxygen, so you have a partial pressure of 0.20 atmospheres of oxygen. And then 1% of it is argon, so you end up with 0.01 atmospheres of argon. Math check, so you just add them all back together, and yeah, it ends up being 0.95 atmospheres. Now there is another law that I typically only use for my advanced chemistry students, and that is Graham's law of effusion. What effusion is that it is the passage of a gas through a small opening into a new container, as compared to diffusion, which is just where you have gas particles mixing together. So the equation is the velocity of gas 1 divided by the velocity of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. And this whole thing is due to the fact that heavier gas molecules are going to travel more slowly at the same temperature than lighter ones would. So then we just define these different variables. You say, all right, need an example. So how much faster will helium travel than methane, CH4, at a particular temperature? So molar mass of gas 1, we're going to say that's the helium. Molar mass of the CH4 is 16 grams per mole. So we plug in the numbers and we see that the ratio of gas 1, helium, to the methane, gas 2, works out to be 2. So that tells us that helium travels twice as fast as methane does. So that's all I have to say about gas laws. Thank you for listening.